Okay, so it is good to see everybody. So you probably heard or noticed we're not doing the activity today. Something came up and I'm having to rearrange the schedule a little bit. So we're going to do the activity on Monday. That means the homework days that we were going to discuss are going to be switched a little bit. Tuesday is when we'll talk about 1.7. Um, Wednesday is when we'll go ahead and talk about 1.8. We just wrapped that up yesterday. You'll still have your exam next week on Thursday the 30th, so that's going to cover 1.4 to 1.7. You got your index card, whatever you want to put on the front and the back to help you out, whether that be, I don't know, multiplicity, could be something with the characteristics of a polynomial, factoring, anything along those lines. Okay, so that left the question, okay, what are we going to do today? So I did have this filed, and it's actually the first time I've used it. I didn't get a chance to use it last year. This is what we refer to as a Pick 6. And this one is perfect. It covers material from 1.4 to 1.6, which is the majority of your exam next week. So there are 6 questions. So I'm saying for today, let's at least go through 4. If we go ahead and talk through 4 together, we'll be done for the day. We'll get to SEL, and then we have ourselves a good weekend. Okay. And I mean, if we get to the 4th one and anybody wants to look at the other, 2, we can, because that's the best SEL. But, okay, we'll see. So, which problem would you like to begin with first? What? Let's just start with 1. Okay. So, factual recall. It says for the polynomial function 5x to the 4th minus 9x cubed plus 3x squared minus 9x minus 2, we want to identify the following. Okay, so I'm just going to go around the room and people help me out. So the degree of the polynomial, Audrey, it is 4. Remember, the degree is the largest power that any one term has. Okay, so the degree is 4. Okay, Vera, the leading coefficient, 5. Because that's the coefficient of the term that gave me the degree. Okay. Right. What about the constant? -2. So the constant is the numerical value that has no variable. And D, a 0 of the polynomial function P if x minus 2 is a linear factor of P. Okay. Akil, what do you think about that? It is 2. Because what we do is set this equal to 0 and we'd solve for the root. There you go. That's 1 down. What next? 6. 6 is a good one. Okay. Now 6, it says Sophie attempts to find the zeros of the polynomial function. Okay, so x to the 4th minus 2x squared minus 3x minus 2. Sophie graphs the function on her calculator and states that the function has exactly 2 complex zeros. Explain what's wrong with Sophie's statement. Write a correct statement about the complex zeros. Now, here's the thing. How would we typically go ahead and find the zeros? What would we do with the polynomial if it wasn't already done for us? We would factor it. Now, we've talked about a 4-term polynomial before. We would go ahead and use grouping. Unfortunately, grouping isn't going to work on this one. We would have to go ahead and use either long division or synthetic division to go ahead and break this apart. Now, since we haven't talked about either of those yet, I'm going to wait on those topics, but I will just go ahead and give you the factored version. Once you break this apart, here's what you should have. So x minus 2 times x plus 1, and then you should have x squared plus x plus 1. Okay. So if you were to multiply all of that back together, you're going to get right back to Q where we started. So does anybody think they might be seeing what's wrong with Sophia's statement? Okay, well, let's take a look at the graph. Maybe that'll help out. Okay, so what do we got here? X to the 4th minus 2x squared. Okay, so x to the power of 4 minus 2x squared. Was it minus 3x minus 2? Okay, all right. So here's my graph. So I'm looking at this. What are my 2 roots? -1 and 2. So if I were to come back over here to the factored version that I provided you, we do see setting these equal to 0, I would get a +2 and the -1, right? Okay. So that leaves this right here. Okay, we would still need to go ahead and take a look at it. All right. Well, let's see if we can do it by hand. What two numbers would multiply to give me 1, but then turn around and add to give me 1? Okay. Is that even possible? It's not possible, so this is prime. Now, that doesn't mean we're not going to be able to get a solution out of it. You might remember from Algebra 2, there was a lot of different ways to figure out the roots of a quadratic. Just for the sake of time and efficiency, because I think this is probably one of the fastest, we're going to use this. The opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, you know that as well. That's the quadratic formula. So let's see, just this is kind of FYI, see if you remember the terminology. Does anybody remember what we call the radicand b squared minus 4ac? It was a bigger word, started with a D. It is the discriminant, yes. Okay, only a handful of people have gotten that today. Very good, very good. So let's go ahead and start to figure everything out. So b squared minus 4ac, all right. Well, b, okay, this is b, this is a, this is c. All right, so b squared would be 1 squared. Minus 4 times a is 1, c is 1. So looks like 1 minus 4, my discriminant is going to be -3. Okay, so the opposite of b, so -1 plus or minus the square root of -3, all divided by 2 times a, 2. See, that's why I love the quadratic formula. It's so fast. Okay. Now, the only thing I have to take care of, remember when you're taking the square root of a negative, that's when it goes imaginary. So here we go. X equals -1 plus or minus I root 3 divided by 2. Okay. So how many solutions do I have there? Okay, right here. How many do I have? 2. How do I know that? There you go. I know because of the plus minus. Okay. Well, come back up to the statement. This is what's wrong with Sophia's statement. Okay. There aren't 2 complex zeros. How many complex zeros are there? Anybody got a guess? There are 4. Okay. And I already see some people go, huh? Okay. There are 4. See, we got 2 solutions here. Okay, 1, 2, 3, 4. So there are 4 complex zeros. Okay, so people are probably wondering, wait, why are we counting those? Because typically people only tend to think imaginary or complex if you actually see the imaginary unit, right? Okay, well, let's think about the hierarchy. Okay. If we're looking at the group of real numbers, does anybody remember what 2 groups make up the real numbers? Starts with R. Rational and what? Now, so here, natural is a subgroup or a subset. Okay, so Q, okay, and then Q/R. Okay, we say Q/R. We don't use I. You might have been taught at an early age that I would be irrational, but when you get to higher mathematics, we don't use that anymore because then I, it goes for imaginary, and then it goes down. We have the integers and whole numbers and natural numbers, right? Well, there's a larger group that the reals belong to. Okay, the complex. Okay, so the complex numbers are made up of the reals and your imaginary. Okay, so because of this hierarchy, okay, any real number is considered a complex number. Okay, so those are still considered complex. So that's why we have 4. And remember, it also brings up a good point. I brought this up during the lesson, but I want to go ahead and make sure to kind of emphasize this. Remember, it is very possible for a graph to cross the x-axis and still have imaginary solutions. In fact, here's an example right here. Okay. All right, does that make sense? I'm glad somebody asked about that one. That one I would think is probably the most difficult on this page. Okay. All right. All right, what's next? That's 2 down, 2 to go. 5. Let's look at 5. Okay, so the figure shown is the graph of the polynomial function m. So A, write an expression for m in factored form using A as the leading coefficient. All right, so I'm going to go ahead and start this off. So m of x equals. So we have this leading coefficient A. I want you to go ahead and finish that for me real fast. Now, just so that we're all on the same page, looks like I have 3 roots, right? The first one being -2. What else? We got 0 and 3. Okay. So remember, we're looking to write the polynomial in factored form. Okay, so I want to give you a second to think about that, and then we'll go ahead and talk about it. Okay, is everybody about ready? Okay. Now, think about it this way. If we have the factored version, we set those groups equal to 0, and that's how we find the roots, right? Well, here we have the root. Like, for example, we know one root is x equals -2. Well, why don't we work backwards to get that group? So if I add 2 to both sides, see, I have x plus 2 is equal to 0. Okay, so that's going to be one of my groups. Okay. Now, there's something about this group that we got to come back and deal with in just a second, but let's go ahead and get the other ones. We can do the same thing for 0. Now, here, you're more than welcome. I mean, x equals 0 is just x. You're more than welcome to just put x, but for this one, I think I'll just go ahead and put the x minus 0. Doesn't change anything. So what would the last group be? What group would give me a positive 3? X minus 3. Okay. Now, we're almost done. Why did I say we have to come back and look at this one? Why? There we go. See, you remember multiplicity. If we're taking a look at -2, it doesn't cross the axis, it hits it, bless you, and it bounces off. So it only does that if it has an even multiplicity. So all we know, maybe it's squared, maybe it's to the 4th. Since we don't know without a little more analysis, we're going to go with the smallest one possible. Okay. Now, if it has an odd degree, then it will cross at that location. You see, it crosses at 0 and 3, and we've already got powers of 1, so that's perfect. Okay. All right, so there we go. How many people got that? Yeah.
Could you just write a times x and then the x plus 2?
Oh, ax and then x plus 2, x minus 3? Perfect. Perfect. Okay. All right. How many people got that one right? Okay. Does it make sense? Okay. Well, let's take a look at B, and this is where we'll need a calculator. Which value of A in the list below displays a polynomial that best matches the given graph of M? So basically, if I were to go ahead and take any of these 4 and plug it in for A, which one's giving me that graph? Well, just based on the characteristics, there's already 2 answers that I can get rid of. Remember, think about your end behavior. We got a polynomial where both the left and the right side are going down. Okay. What kind of leading scale factor would give me that? It would have to be what? It would have to be negative. Okay. So that means there's no possible way it could be positive. If it were both going up, then it would have to be one of the positives. Okay. Well, let's go ahead and plug this in with, let's start with -0.2. Let's see which one works out. So it looks like this one right here, probably getting close to 7 for that relative max. Okay, so we have, let's get rid of this. All right, so we have a negative 0.2 times x plus 2 times x. I'll just put x this time. And then x, what was it, minus 3? Okay. There we go. So I'm going to go ahead and push enter. Oh, I see what I forgot. Come on. There we go. I forgot the squared on that one. Okay, so let's put the squared in there. That's better. Okay. So that pretty much looks exactly like the graph I have, but let's just be sure. Let's go ahead and put in the other coefficient to see what happens. So right now the negative 0.2 is looking pretty good. Okay, so let's go in here. Let's change that 0.2 to a 3. Okay. So what do you think? They both have the same general shape, but which one's going to work better? I'd say the negative 0.2. This negative 0.3, that relative maximum, it looks like it's just going to be too high, much higher than it was on the paper. Okay, here we go. All right, one more. 2. Okay, let's do 2. Okay, so it says carry out a procedure. All right, so for the polynomial function g, find the zeros and their corresponding multiplicities. Okay, well, this one's already factored for me. So I'm going to go ahead, set each one of these groups equal to 0. Okay, so Quinn, can you tell me what the first root is? It is negative 3. And what's its multiplicity? Here we go. Remember, the multiplicity is the degree of the factor. Okay, so in this case, 3. All right, well, what's the next root? Negative 1, which has a multiplicity of 2. And finally, the last root, 4, with a multiplicity of 4. Okay. Is everybody okay with that? Now, B, at which of these zeros is the graph of the polynomial tangent to the x-axis? So remember, when we see that word tangent, we're talking about one point of intersection. So basically, at which of these zeros would it not cross? Would it hit the axis and bounce off? What do we think? Negative 3, negative 1, 4. Negative 1 and 4. Why? Okay, because both of those have an even multiplicity. Remember, if it has an even multiplicity, it will not cross at that location. If it has an odd multiplicity, it will cross the x-axis. Okay? And I said if we got through 4, we'd be good to go, but I do have to ask. Either of the remaining 2, is anybody curious or want to talk about it?
Are we doing the remaining till Monday?
No, this is just kind of like review for you. Do you want to do it?
Can I do 4?
You want to do 4? Let's do 4. Okay. So let's see here. Prove, show, and justify. For each of the polynomial functions, write appropriate limits to describe the end behavior. Give reasons for your answers. Okay. So I'm going to write this down here where I have a little more room. It doesn't say it specifically, but let's go ahead and write out the limit statements. So for part A, I'm looking to find the limit as x approaches negative infinity for f of x, and then the limit as x approaches positive infinity for f of x. Okay. So we're going to go ahead and provide the limits first, and then I want you to tell me the reasoning. Okay. So let's see. The left end, as x approaches negative infinity, what should happen here? What's my answer to that one? Anybody know? It is positive infinity. Okay. What about the limit as x approaches positive infinity, the right? Positive infinity. Both of these would be positive infinity. How do we know that? That's exactly right. Look at the combination of your degree and the coefficient. We have an even degree with a positive leading coefficient. Remember, if it's an even degree, both ends are up or both ends are down. Okay. That's exactly right. Okay, so try B. Okay. Try B on your own. Go ahead and erase this real quick. Because now we're dealing with h of x. This is B. Negative 6x cubed plus 2x minus 4. Okay. William, what do you think about as x approaches negative infinity? Positive or negative infinity? Positive infinity. Okay. And Reed, as x approaches positive infinity, positive or negative infinity? That should be negative. Okay. And the reason is we have an odd degree. So the ends are going to be going in different directions, and this one has a negative leading coefficient. Okay. Remember, if it's odd with a positive, it is down on the left, up on the right. Okay. So I'm ready to stop unless anybody wanted to do number 3. You would be the first class to go through all of them. Okay. There we go. There we go. All right. Let me get that set back up.